Let me welcome you to this lecture. During this lecture, we will discuss the chemistry of another interesting pi-acid ligand. That is um, we will discuss the chemistry of metal phosphine complexes or complexes formed by the phosphine ligand. As such, phosphine complexes are ubiquitous, and there are many phosphine complexes that are known so far. And one interesting aspect of metal phosphine complexes with the phosphine ligand is that there are three substituents attached to the phosphorus atom in phosphine ligands, and these substituents can be changed, and therefore the phosphine ligand or the electronic as well as the steric property of the phosphine ligand can be changed, and this allows one to tune the property of metal complexes uh, as required in case of catalysis, and therefore many of these metal phosphine complexes serve as important catalysts. We'll see two examples of metal phosphine complexes which are important catalysts. The first example that we can see is the rhodium phosphine complex, that is triphenyl phosphine. This is known as Wilkinson catalyst, and is a very important catalyst for hydrogenation of olefins. In fact, this is used as a catalyst in industrial processes which require hydrogenation of olefins, the Wilkinson catalyst. Another important catalyst that involves phosphine ligand is the Grab's first generation catalyst, that is a ruthenium complex, ruthenium carbene complex actually, and it contains two ligands, two phosphine ligands, that is tricyclohexyl phosphine ligand. This is called the Grab's first generation catalyst. First generation catalyst, and it is used as a catalyst in olefin metathesis. And in fact, Grab's was the recipient of Nobel Prize in Chemistry in the year 2005 for discovery of Grab's catalyst, which are used as catalysts in olefin metathesis. So these are two examples of metal phosphine complexes which are essentially used in very important catalysis. Now there are many phosphine ligands, and some of these phosphine ligands we have already encountered while discussing the chemistry of metal carbonyl or metal nitrosyl or metal dinitrogen complexes. And phosphine ligands essentially act as spectator ligand. They do not participate themselves in reactions, but they can be used to tune the electronic properties or the nature of the complexes by changing the substituents on the phosphine ligands. That is, we can change both the electronic behavior as well as the steric behavior of these ligands, and we will see how we can do that, of course. But first, let us look at some phosphine ligands or some commonly used phosphine ligands. We have already encountered a very popular phosphine ligand, that is diphenyl phosphinoethane. that is bis diphenyl phosphinoethene. Diphenyl phosphinoethane. Okay. We also call this ligand in short as DPPE here. DPPE, and another commonly used abbreviation for this ligand is also diphos, because there are two phosphine ligands in this. It is a bidentate phosphine ligand, and that is why it is also abbreviated as diphos. You can change the subsequence of the phosphorus atom here and then obtain a different diphos ligand here. That instead of phosphine ligand, you can also use methyl substituents of the phosphorus, and then it is dimethyl phosphinoethane, or in short DPPN. There are also ligands for the such bisphosphine ligands which are chiral. So for example, you can use chiral ethanes instead of non-chiral ethane, and then you can have chiral phosphine ligands or chiral diphos ligand, and that is why this ligand is essentially again abbreviated as chira diphos. There is another interesting chiral diphosphine ligand which is again commonly used in many catalysts. That is, it contains the bis-naphthalene group here and the phosphine. So this is known as binap. It is abbreviated as binap ligand. Again, very important or very commonly used ligand to prepare active catalyst for many reactions. Now we have already discussed that the phosphine ligand or the subsequent on the phosphine ligand can be changed, and this essentially allows us to change the electronic behavior as well as steric behavior. To understand how it can be used to how these substituents can be used to change the electronic behavior of the phosphine ligand or electronic nature of phosphine ligand, we'll look at the nature of bonding in metal phosphine complexes first. The phosphorus atom in metal phosphine ligand is sp3 hybridized, and it uses three of the sp3 hybridized lobes to form bonds, sigma bond with the substituents, three substituents, while one of the sp3 hybridized orbital contains a lone pair of electron, and essentially the the phosphine ligand donates this lone pair of electron to metal orbitals of the appropriate symmetry to form metal phosphine sigma bond. So this pair of electrons are essentially donated to metal orbitals to form metal So this is sigma bond, where the phosphine ligand acts as the donor now to empty metal orbitals. Now the phosphine ligand also acts as a pi acceptor, as it can accept electron density from filled metal orbitals to sigma star orbital of the phosphine ligand, that is sigma star orbital of the phosphine ligand, we can draw in this way, which is empty, that is sigma star empty sigma star orbital on phosphorus on phosphine ligand, and it can now metal orbitals or filled metal orbitals can now donate electrons to this sigma star orbital of phosphine ligand, and that is how the phosphine ligand essentially acts as a pi acceptor ligand now, and it forms the metal to phosphorus bond. The bond order is more than one, because apart from the sigma bond that is formed by the donation of electron from the lone pair of electrons from the phosphine ligand to the empty metal d orbital, there is also pi back bonding from metal filled metal orbital to empty sigma star orbital of phosphine ligand. Now we have seen when we discuss about the pi acceptor ability of different phosphine ligands, we have seen that PS3 is a better pi acceptor than PME3 or PPH3, and the reason we can find out by looking at the energy of these or the energy of this uh, metal phosphine, the phosphine sigma star orbital. So in case of molecular orbital formation, in case of the uh, phosphine ligand, so phosphorus orbitals will combine with orbitals of the substituent here to form, say, in this case, let us assume that carbon, which is is the donor atom, in case, which is the atom with which phosphorus form bonds. In case of say PME3, will form molecular orbitals in so this is the sigma star orbital for phosphine ligands, in which there is phosphine to carbon linkage with the substituent here, and this is the sigma PC. Let's write it in this direction. That is bonding PC, which is going to be filled, and anti-bonding PC, a molecular orbital, phosphorus carbon molecular orbital, uh, that is going to be empty, and where phosphorus can accommodate electrons from metals while forming the pi backbone. Then, in case of when we have a substituent which has more electronegativity than which is more electronegative than carbon, then the energy of those orbitals will be lower than the energy of these orbitals of carbon. And say, for example, for nitrogen, the orbitals of nitrogen which form sigma as well as sigma star molecular orbital with phosphorus orbital will be located at energy lower than the corresponding orbital of carbon, which forms the sigma star molecular orbital. So then, in case of in case the substituent has nitrogen atom is linked to the phosphorus here, then in those cases the sigma star orbital, that is sigma Pn in this case, will be located at lower energy than the sigma star PC molecular orbital, and the sigma Pn will also be located at lower energy than the PC orbital. So this is sigma Pn. Now for substituents which contain oxygen atom, or in which cases the oxygen atom is bonded to the phosphorus atom over here, in those cases again oxygen corresponding orbital of oxygen will have lower energy than even orbitals of nitrogen, because oxygen is more electronegative than nitrogen. And again we can draw a sigma star PO is going to be here, while sigma PO will be here. And for more electronegative substituents like fluorine, as in case of PF3, will have even lower energy, and in those cases, again, that is sigma star PF is going to be located here, while sigma PF will be here. So what is obvious from here that the sigma star orbital have lower energy when the substituent on the phosphorus atom is a more electronegative element like fluorine. We see that the sigma star molecular orbital to which the metal donates electron to donate electron during pi back bonding is located in lower energy only when the substituent is more electronegative. So when the energy of this sigma star molecular orbital is low, metal can donate electrons more efficiently to the sigma star molecular orbital, and that is why PF3 acts as a better pi acceptor than say PME3, in which case the sigma star molecular orbital, the orbital which is going to accommodate electron density from the metal field orbital, is located in higher energy, and that is the reason why phosphine ligands like trimethyl phosphine or triphenyl phosphine, where carbon atom is essentially attached to the phosphorus atom, are poor pi acceptor than trifluorophosphine or trichlorophosphine ligands, where we see that the electronegative atom is attached to the phosphorus atom. Also, one more reason why such PF3 or POME3 acts as a better pi acceptor than PME3 or PPH3 is you see that the sigma star molecular orbital is more localized on phosphorus atom when the phosphorus atom is attached to electronegative element, because the energy of the sigma star orbital is more close to the energy of the phosphorus atom only when it is attached to the phosphorus atom is attached to an electronegative element, and that is the reason that on the sigma star molecular orbital, this molecular orbital is localized on phosphorus atom, and that is why metal can donate electrons, or when pi back bonding takes place, it can efficiently transfer electrons from metal orbitals to phosphorus orbital, or an orbital which is more localized on the phosphorus atom, and the transfer of electron density during pi back bonding is more efficient. And this is also another reason why PF3 acts as a better pi acceptor or phosphine ligands, where electronegative substituents are present, acts as better pi acceptor than those cases where the substituent contains atoms which are less electronegative, or substituents like say carbon or nitrogen. So now we know how we can uh, enhance the pi acceptor ability of phosphine ligands, and this allows us to design metal complexes with better pi acceptor capability to the metal, or you can tune the pi acceptor ability of the phosphine ligands, and accordingly you can design catalyst. Another reason why phosphine ligands are used extensively in catalysis is because these ligands, when we change the substituent on the phosphine ligand, we can also change the steric behavior property of the ligand. Now, when we have ligands like CO or dinitrogen or nitrosin, which are sterically not very demanding, so as we see carbon monoxide or dinitrogen or NO, these pi acceptor ligands which we have discussed, they are not sterically very demanding, and that is why we can have as many ligands as required to satisfy the 18 valence electron rule. But when you have ligands like sterically demanding substituents on the phosphorus atom in case of the phosphine ligand, now metal will have difficulty to accommodate too many sterically bulky ligands around the metal center, and that is why one may not be able to satisfy the 18 valence electron rule when sterically bulky phosphine ligands are present in the complex. And we will see examples where this is happening. But before that, what we should see is that there is a way to measure the steric bulkiness of a ligand, and that is called the Torments cone angle. One can measure how bulky a particular phosphine ligand is by measuring the cone angle, and this cone angle is known as Torments cone angle. So when we take a metal phosphine complex, that is metal here, phosphine, and the substituents of the phosphine ligand, now we can consider a cone angle, that is by taking the metal at the apex. So the solid angle formed by the metal at the apex and the outermost edge of the van der Waals sphere of the ligand atoms at the perimeter of the cone. Is known as the Torments cone angle. That is, we look at the van der Waals sphere of these ligand atoms at the outermost sphere of the edge of the van der Waals sphere of the ligand atoms, and then we consider a cone starting from the metal, that is metal will be at the apex, and one can now consider a cone. So this is the cone that we generate by considering the metal at the apex, and when we consider the perimeter of the cone at the outermost edge of this van der Waals sphere of the ligand atoms here in this way, in this fashion, and this angle now, which is the cone angle, is known as the Torments cone angle. Now this is a measure of steric bulkiness of the ligand, because if you have more bulky ligands, the cone angle is going to open up and they will have a larger cone angle, and for ligands which are not so bulky, the cone angle is going to be smaller in this case. So just by looking at the cone angle or by comparing the cone angle, we can compare the bulkiness of two phosphine ligands. Now we have already discussed that for ligands which are sterically non-demanding like carbonyl ligands, we can have as many ligands as required by the 18 valence electron rule, but that may not be true for when we have sterically bulky ligand in the complex. So the 18 electron rule may not be satisfied, because you cannot put too many ligands around the metal center to satisfy the so that you can attain the 18 valence electron count. Now we will see examples of complexes where this happens. So for example, if you take molybdenum, say CO6, and then do substitution reaction of these carbonyl ligands by using phosphine ligand. That is, if we prepare now PR3, and we can replace 3 of the carbonyl ligands by 3 phosphine ligands if the phosphine ligand is not sterically bulky or the cone angle is low. For those phosphine ligands like PH3 or PME3, we can replace the 3 of the carbonyl ligands and then prepare MoCO3 PR3 3. So that is not a problem, but when you use sterically bulky phosphine ligands, so for example, if we use isopropyl phosphine ligand, where in this case isopropyl is a quite bulky ligand with large Torments cone angle. In this case, we will not be able to replace, or we will not have 3 phosphine ligand in the resulting complex. Even when we substitute 3 carbonyl ligands and the complex, we have only two phosphine ligands. Though we substitute 3 carbonyl ligands instead of 3 phosphine ligands, as we see in case of sterically less bulky phosphines. Here, in case of this isopropyl phosphine, when we do the substitution reaction, only 2 phosphine ligands are present in the resulting complex. Now, there is this particular complex. If you do electron count, you will find out that it contains 16 electrons or valence electrons only, and it does not satisfy the 18 valence electron rule. So there is coordination unsaturation in this particular complex, but this coordination unsaturation cannot be fulfilled by the bulkier isopropyl phosphine ligands, and that is why the unsaturation remains. But if you use now sterically less bulky ligand, so for example, if you do reaction with dihydrogen, which is sterically less bulky, and now one can fulfill the coordination unsaturation in this, and a 18 valence electron species can be prepared in this way. So in this case, the dihydrogen ligand is present in this complex, and the coordination unsaturation is fulfilled because dihydrogen is a sterically less bulky ligand, and that is why it can now be accommodated around the metal center. And if you look at the structure of this complex, what you will see that the 2 phosphine ligands are trans to each other, while the dihydrogen ligand is coordinated to the metal center in this fashion. So now dihydrogen can occupy the coordination site on the molybdenum center because it is less bulky and it can be accommodated around the metal center. So another example where we see the relevance of static effect in metal phosphine complexes is that if you use less bulky ligands, phosphine ligand, then you can prepare 18 valence electron complexes like this here, say triethyl phosphine. If you use, then you can prepare 18 valence electron platinum phosphine complexes where there are 4 phosphine ligands. But when you use sterically bulky phosphine ligand, instead of such complexes, you will not have that 4 phosphine ligand in the resulting complex, and instead what you will have, say if you use such a butyl phosphine ligand, only 2 phosphine ligands can be accommodated around the platinum center, and it's now you are not able to isolate the complex 18 valence electron complex as you do in case of the triethyl phosphine ligand, because now again the phosphine ligand is sterically bulky and it does not allow 4 ligands to be accommodated next to the metal center. One more example where we see the steric effect of the phosphine, sterically bulky phosphine ligand is when we prepare this sort of metal phosphine complexes where there are two phosphine ligands, and in this case, though when you prepare this complex by substitution reaction from MoCO6 with phosphine ligand, first you do substitution of one of the carbonyl ligand. Now, because this phosphine is a poor pi acceptor than carbonyl ligand, this metal to metal carbonyl bond distance or bond, metal carbon bond, which is trans to the phosphine ligand here, will be strengthened because this carbonyl ligand can now accept more electron density from the molybdenum center as compared to the other carbonyl ligands, because this is trans to a ligand which is 4 pi acceptor. This particular metal carbon bond is strengthened in this, and you expect, or one expects, that now the next phosphine ligand, when we will add the one of these carbonyl ligand which is cis to the initial phosphine ligand will be replaced, and one will obtain a cis complex. So electronically, a cis product is favored, and indeed, when you do such a reaction with sterically less bulky ligand, the percentage of cis product isolated is more. But when you use sterically bulky ligands, the percentage of trans product, that is so the trans phosphine complex becomes a major product when you use bulkier phosphine ligand, and we know that this particular product is not electronically favored, but it is formed in larger quantity because now two sterically bulky phosphine ligands cannot be accommodated cis to each other in this metal complex, and therefore the trans complex is, or the trans product is now favored and forms in as a major product. So this essentially brings us to the end of this lecture. We have discussed about metal phosphine chemistry. We have discussed about phosphine complexes which are used as catalyst, and we have also discussed about commonly used metal phosphine ligands, and we have also discussed the bonding of phosphine ligand with metals, and we have seen how the field the unpaired electron in phosphine ligand can be donated to metal to form the sigma bond, while metal to phosphine pi back bonding can happen by transfer of electron density from filled metal orbital to sigma star orbital of the phosphine ligand, and this also explains why when more electronegative substituents are present in the phosphine ligands acts as a better pi acceptor. We have also discussed about the steric bulkiness or the measure of steric bulkiness in metal phosphine complexes, and we have seen the Torments cone angle, or discussed about Torments cone angle and how it can be used as a measure to discuss the reactivity of these metal phosphine complexes. That in some of the cases, when we see that when we have bulkier phosphine ligand, we are unable to isolate 18 valence electron complexes because it is not possible to accommodate too many bulky ligands next to the metal center, and this does not allow us to isolate 18 valence electron species. Also, we have seen why in some of the reactions here we isolate trans product, which is not electronically favorable, but it happens because it is because of the difficulty in accommodating two phosphine bulky phosphine ligands cis to each other in these complexes. So with this, let me conclude this lecture. I thank you very much for being with me during this lecture.